We are now moving on into Chapter 4. Chapter 4 is going to consist of specific types of chemistry having to do with specific types of reactions. But in order to understand reactions, we need to understand how reactions take place. Now, most of you know that if you have a cake batter sitting on your turnabout or on your shelf at home in the cupboard, that cake batter, even though it's filled with all kinds of different chemicals like sodium bicarbonate and tartaric acid and things like this, it won't react unless those liquids are added into it. Then you can bake yourself a cake. So, what we need to talk about is this idea that we need to have these chemicals, these different molecules and compounds in some kind of liquid so that they're free to move around and interact and react with each other. So we're going to start by talking about water because water is the most common solvent. You'll see here the first line says recall that solutions contain a solvent and a solute. You're not going to recall that because you haven't been taught that yet. What this means is we have a beaker. In that beaker, we have some kind of fluid, some kind of liquid in this case, although solutions can also be solids or gases. But in this case, we're going to have some kind of fluid, and that fluid in this case is water. Water is a solvent. It means that it can dissolve things in it. Those things that get dissolved in it are called solutes. So an aqueous solution then is a solution in which the solvent is water. And on all of those practice balancing equations, you guys saw things in parentheses after some of the formulas with the AQ. The AQ means aqueous solution. Now, as I said, solutions don't have to be liquid. They can also be gases or they can be solids. If you have something like brass or steel, those are also solutions. They just happen to be solid solutions. Air is a solution. Now, how can you tell the difference between the solute and the solvent? The solvent is what is occurring in the highest percent or the highest amount. So in the case of air, 70 some odd percent nitrogen, nitrogen would be considered the solvent. Everything else would be considered the solutes. In most aqueous solutions, water is your solvent, the rest are the solutes. Now, water is unique. It has the ability to dissolve many types of substances. It also has a lot of other unique properties, such as specific heat. Specific heat is why it's cooler towards the lake in the summer and warmer towards the lake in the winter. There's also other properties that the density of it, things like that, that make water unique. But because this is chemistry and we're dealing with solutions right now, the solution part is what we're going to focus on. Now you'll notice that water here has some covalent bonds to it. Those covalent bonds means that the electrons are shared. Now hydrogen only has 2 valence shell electrons when it's sharing one of them with oxygen, and it's very happy with those 2. But what it does is because oxygen is so electronegative, it means it likes a lot of electrons, and it has these spare pairs of electrons out here on the side. Those electrons from hydrogen are held closer to the oxygen than they are to the hydrogen. And because of that, it creates the situation where there is a slightly positive end of the water molecule and a slightly negative. So this little guy here means slightly. So water is very important to us because it is kind of polar, kind of ionic, but it's also kind of nonpolar, well, it is covalent. But because of this, we can say that it's what we would consider the most universal solvent because it can dissolve things that are ionic and things that are covalent. So it's a polar molecule. Polar, like North Pole, South Pole. Here we have a positive N and a negative N. So it's kind of like poles on a magnet or poles on the Earth. It occurs when there's an uneven sharing of those electrons in the covalent bond, and that helps it dissolve that wide variety of substances. Now, hydration is really just dissolving, but I'm going to draw you a picture to show you how this works. So this is what a sodium chloride block of salt would look like if we could look at it on the atomic level. Sodium is a very small atom. Those are the little guys in between. Chlorine is a very large atom. Those are the guys on the outside. Now what happens is water comes up to it. And because water has these positive ends and these negative ends, the positive end is going to be attracted to that chlorine. And if you get enough water molecules who are following in line and doing the same thing, it will surround that chlorine or that chloride ion, and the force between that hydrogen, that positive side of the water molecule, and the negative chlorine is going to be greater than the force that is holding together the sodium and the chlorine. And when that happens, then that guy gets carried away. So eventually these guys will encapsulate the chloride ion and it'll get carried away. Then the oxygen end of the water molecule will come in and it'll be attracted to the sodium. Again, when there's enough water molecules, it will pull on that sodium with more force than the hydrostatic force that's connecting the hydrogen and the chlorine, and the sodium and the chlorine, and it'll pull that sodium away. So that's really what dissolving is when you're talking about ionic compounds such as salt. Here they call it hydration, the process in which the negative ends of a water molecule are attracted to the positive ions. Positive ends of the water molecule is attracted to the negative ions. The result is that the ionic compounds fall apart. And how easily those break apart is called solubility. So solubility depends on the attraction of each constituent ion for each other. Some things are very soluble in water, some things are not so soluble in water. It depends on its attraction for each other within the ionic compound and its attraction for water. Now, there are also cases where we have nonpolar substances, and sometimes the molecules will have polar parts to them so that they can still be dissolved. So for instance, if I draw methanol here, methanol is really a nonpolar compound, but because it has this oxygen sitting here with these ions, it will still get torn apart by the water because the water can swoop in and connect onto those oxygens and get it to fall apart. However, this is not an ionic compound. So what happens instead is that you get the individual molecules being pulled away from each other. Think about sugar. Sugar is chains of carbon. Sorry, should be a 6-member chain. They have oxygens sitting on them in different places, and I don't know exactly where they are, so we're just going to throw some on there. When sugar dissolves, we're not pulling the oxygen atoms off or the carbon atoms off using the water. We're just simply pulling the molecules away from each other. So the sugar dissolves because the block of sugar has all of these molecules in it, and the water is taking those individual molecules away and having them dissolve. They're to the point where you can no longer see them then. So that is, in short, why water is so important. It has these great properties that allow things to be dissolved in them. If we can get these ions or these individual molecules away from each other, then they're free to roam and they're free to interact and cause chemical reactions.